This set of notes is going to cover sections 6.7 to the end of chapter 6. We're going to begin our discussion of polar reactions. Polar reactions involve ions as reactants, intermediates, or products. So within these polar reactions, we have negative charges or partial negative charges being attracted to positive charges or partial positive charges. That means electron-rich species, something that could be an anion or something that has a partial negative charge, will be attracted to a cation or something that has a partial positive charge. These reactions involve electrophiles and nucleophiles. Electrophiles are electron deficient centers, and nucleophiles are electron-rich centers. So the carbon here would be the electrophilic site. The carbon on this molecule would be the nucleophilic site. A nucleophile is simply an electron-rich species that can donate a pair of electrons to form a new bond. Nucleophiles are considered Lewis bases, electron pair donors. The more polarizable an atom is, or the ability of its electron cloud to be distorted, the stronger the nucleophile. So nucleophiles are going to be things that have negative charges. They might have partial negative charges. And they're attracted to positive charges or things that have partial positive charges. So if you look at the carbon here, it has a partial negative charge because the lithium metal atom has a much lower electronegativity. So carbon being more electronegative than lithium gives the polar bond, and carbon becomes a electron-rich species and makes it a good nucleophile. The ethoxide ion is also a good nucleophile because we have an atom with a negative charge. So partial negatives make good nucleophiles, and negative or formal, a full formal negative charge makes a good nucleophile. If you look at ethanol, ethanol has an oxygen atom with a partial negative charge, also a good nucleophile. And alkenes, or carbon-carbon double bonds, can also act as nucleophiles. So I mentioned polarizability, and larger atoms are more polarizable. So S2 minus is a better nucleophile than O because S is larger. Electrophiles are anything that have an electron deficient site. These can accept a pair of electrons from the nucleophile that donates them. Electrophiles are typically Lewis acids. Carbocations and partial positive atoms are typically going to be your electrophiles. So the electrophilic site on the first molecule is our carbon atom because it has that partial positive charge. You're going to see very common electrophiles are alkyl halides. And that's going to be the focus of chapter 7. Also, anything that has a full formal positive charge can be an electrophilic site. And the reason is because any carbocation that has lost an electron basically emptied its p orbital. So as an empty, unhybridized p orbital that is electron deficient and readily reacts with a nucleophile. Anything that has a it can donate electrons. In this example, we're going to identify all the nucleophilic and electrophilic sites in the molecule. So let's look at carbon or oxygen atom 1. We have two lone pairs of electrons. This is a polar bond, partial negative, partial positive. Since the oxygen has a partial negative, it's a nucleophilic site. We look at carbon 2. That's the carbonyl carbon in a polar bond. Carbon has the partial negative, oxygen has the partial carbon has the partial positive, oxygen has the partial negative. So anything that has a positive or partial positive charge is considered an electrophilic site. If we look at oxygen atom labeled 3, okay, again, we said that has a partial negative charge. Anything with a partial negative or a full formal negative charge is a nucleophile. We look at the nitrogen in 4 has a lone pair. Also involved in a polar bond, the nitrogen gets the partial negative, the carbon gets the partial positive. So that is nucleophilic. This carbon here, labeled 5, carbonyl carbon, also a polar bond. The carbon has a partial positive. So therefore, we have an electrophilic site. Let's look at 6. If you recall, we said alkenes can act as nucleophiles. This one in particular, if you draw the resonance, you can see that the negative charge can end up on the carbon when we push the electrons through. That's an allylic lone pair pattern. And for 7, we have a full formal negative charge on the oxygen. It has an extra electron, so with a negative charge, that makes it a nucleophile. In section 6.8, we're going to discuss mechanisms in arrow pushing. Now, we've already talked about this in chapter 3, when we did acid-base mechanisms. So if you recall, this was the first mechanism. The base attacks the hydrogen, and then we have to draw a second arrow that breaks the hydrogen acid bond. Okay, and you can see the flow of electrons is denoted by the arrow. The arrow points to where the electrons are going. The arrow starts, the tail of the arrow starts where the electrons currently are. So there's 4 main patterns that we're going to be using, and you need to learn and practice these patterns. The only way to really get this is to practice these. So our 4 main patterns that we're going to be looking at are nucleophilic attack, loss of a leaving group, proton transfer, which we already know how to draw, and finally rearrangements. These are the 4 mechanisms that are going to be involved in polar reactions that we're going to be looking at in chapter 6 and in chapter 7. The first is nucleophilic attack. Now, nucleophilic attack often requires more than one arrow. Sometimes you only need a single arrow. But the key to this pattern is the tail of the arrow always starts on your nucleophilic atom, and the head of the arrow always points towards the electrophilic atom. Now, if we did not draw this second arrow here, we'd have a problem. We'd have a carbon with 5 bonds to it. You cannot violate the octet rule. So that's the reason why we push the electrons up to the oxygen. The oxygen is more likely to accommodate that negative charge than the chlorine because it's more electronegative. You could also think about this, the alcohol that has the partial negative attacking the carbon with the partial positive. You can think of this in terms of resonance structure. So if you take the electrophilic site and draw that resonance form This is a polar pi bond, one of our resonance patterns. You push the electrons, we get a negative formal charge on the oxygen and a positive formal charge on the chlorine. Then you can take your nucleophile with the partial negative and have the nucleophile attack the electrophilic site. And you end up with the same product. Like we said, nucleophiles can also be pi bonds or alkenes. So if you have your sulfite here, or sulfur trioxide, that's got a partial positive, the alkene can attack that, and the alkene was the nucleophile, and our sulfur compound was our electrophile. The next pattern is loss of a leaving group. So this is a form of heterolytic bond cleavage in which when the bond breaks, see this is showing the bond breaking, and the pair of electrons is going with the bromine. So the pair of electrons is leaving the carbon-bromine bond. Both electrons go to the bromine. So that leaves carbon short an electron. That's a carbocation. So again, this is a polar reaction because we've created ions as products. Sometimes you need more than one curved arrow to show loss of a leaving group as well. So our halide is going to be the leaving group. In almost all cases here that we're going to be observing, the halogen is going to be the leaving group. It's an easy way to identify the leaving group. Just look for the halogen. So the halogen always comes off with its pair of electrons. The next pattern is proton transfer. This is one that you're familiar with from chapter 3. They all require two curved arrows. We have the atom that is acting as the base, attacks the acidic hydrogen. Right. The arrow shows where the electrons start, and the second arrow shows where the electrons are going. So this would be plus H, O, H. A lot of times you won't see that shown. When we deprotonate, sometimes it's just shown as a single arrow, so don't get confused if we're not putting. So here we have the base attacking the acid. Sometimes we don't show this arrow or this compound when it's a solvent that's doing the deprotonation. So you might just see a single arrow. But it's implied that you have some base, usually the solvent, with a pair of electrons that's taking the proton. And when you have this scenario, you're usually going to see just a minus H plus there. Sometimes you need more than the usual two arrows to show the proton transfer, especially if you'd end up breaking the octet rule or exceeding the octet rule. So when we have our hydroxide ion taking the proton and the electrons get dumped into this bond, right? We're going to need to move them through resonance. Now, another way to think about this is if you look down here, the hydroxide takes the proton, and then we could dump the electrons onto the carbon atom. We have this species, but this is a resonance pattern. We have an allylic lone pair. So then we can move the arrows through resonance, and we get our second resonance structure. The final pattern is a carbocation rearrangement. And carbocations can rearrange themselves or switch with a hydrogen or a methyl or other alkyl groups at that to become more stable. So we first need to understand what causes carbocation stability. And that's something called hyperconjugation. So if you look at the neighboring groups, let's look at our carbocation here. We've got our empty p orbital, and the neighboring groups are hydrogen and a methyl. Now, this methyl, if you look here, the methyl has a bond, a sigma bond, with shared electrons between the hydrogen and the carbon. The electrons from this sigma bond can be donated and shared with our empty p orbital. And this helps to stabilize the empty p orbital. Now, a hydrogen cannot do that, but this methyl group can. So the more substituents, the better you can stabilize the carbocation. So if this was a methyl instead of a hydrogen, we could get additional stabilization. And then if this was a methyl, we could get even more stabilization. So the more substituents you have around your carbocation, the more stable it will be because of something called hyperconjugation. And that's just when neighboring groups, through slight orbital overlap, can help to stabilize that carbocation. And this explains the trend in carbocation stability. So if you look, the least stable carbocation is a methyl cation. The most stable is a tertiary carbocation. Why? Because the carbocation has the most substituents around it. There's 3 substituents. And because of hyperconjugation, the substituents can donate electron density from their sigma bonds to that empty p orbital to help stabilize it. So increasing the substitution pattern increases the stability of the carbocation. The sigma bonds can donate electron density to that p orbital. There are 2 types of rearrangements that we're going to focus on. The first is a hydride shift, and the second is a methide or a methyl shift. These shifts can only occur from an adjacent atom, meaning an atom that's next to the carbocation. So here's your carbocation. We only have 2 adjacent atoms. These shifts can only occur from atoms that are directly next to it. What you notice is it's just a switch. If you think of it as a switch and then learn how to draw the arrow, I think it's the easiest way to do this. And I'll tell you how to identify if it's going to switch or not, but that has to do with carbocation stability. However, look at the carbocation and look at the hydride that's shifting. They just switched places. See? If you look here, the hydrogen with its electrons is now on the carbon that the carbocation was on, that the positive charge was on. So basically the hydrogen with its electrons and the positive charge just switched places. And the same thing happens with a methyl shift. The methyl and the positive charge simply switch places. Now, that's what we call a rearrangement. So let's try to understand how this is happening and why, how to identify if it happens. So when we draw the arrow, remember, it's a hydride. Hydride is a hydrogen that has an extra electron and has a negative charge. So that means, unlike a proton transfer, a proton is an H+, that's a hydrogen that has lost an electron. The hydrogen moves with its electron. It takes both of the electrons in that bond, and it leaves this carbon deficient. That's why this carbon ends up with the positive charge. A methide or methyl shift, same thing. The CH3 group moves with its pair of electrons, leaving the carbon electron deficient. Section 6.9 simply talks about identifying these patterns. So the first skill, before you start drawing these, you have to know what you're looking at. So many reactions involve multiple patterns. Multi-step reaction mechanisms are the combination of one or more of our 4 patterns that we've covered so far looking at polar reactions. So if you look at our first reaction, we have the oxygen atom is gaining a hydrogen. So this is classic proton transfer. Loss of a leaving group is our second pattern. So I know that I said that the leaving group is typically going to be a halide. But another good leaving group is a water molecule. So here we have H2O that's leaving. So it satisfies that that positive formal charge on the oxygen. It neutralizes that by taking the pair of electrons with it when it leaves, and we're left with a carbocation. So in this third step, step 1, step 2, step 3, step 4, in our third step, we have a methyl group changing places with a positive charge. That's your carbocation rearrangement. And in the fourth step, we have a bromide with a negative charge attacking a carbon with a positive charge. That's nucleophilic attack. So sometimes we can have multiple patterns in a single step. So in the first example, we have 4 steps and only 1 pattern occurring in each step. But multiple steps can have more than one, multiple patterns can be observed in a single step. So in the bottom example, we have nucleophilic attack occurring with the loss of a leaving group. We have a negatively charged oxygen attacking the partial positive on the carbon, and the chlorine is leaving with its pair of electrons. Whenever you see a carbon chloride or carbon halogen bond breaking and the electrons are getting dumped onto the halogen, that's a pretty good sign that it's loss of a leaving group. So this shows you nucleophilic attack. And that's the loss of a leaving group. So in the previous sections, we learned to identify the patterns. We learned what they are. And the next skill is actually drawing each of the patterns. But before we can get into drawing each of the patterns, let's review quickly some of the rules for drawing curved arrows. First, the arrow needs to start where the electrons are. See how the tail of the arrow starts where the electrons are? So you're looking for a negative charge or a partial negative charge. That's where the tail of your arrow goes. And the head of the arrow, which we'll get to in a moment, is going to point towards the positive or partial positive charge. that would be a nucleophilic attack. So we need to show when we want to, so here's your nucleophilic attack. And our loss of a leaving group we have to show that the electrons in that bond are being transferred to the atom. It's going bond to atom there. So this is, the example below is incorrect because we have the pair of electrons going to the bond, to the atom, excuse me, and then the tail of the arrow drawn from that atom again. Again, the correct way to draw it would be to have the tail of the arrow for the second arrow here starting on the bond where the electrons are, and they're going to the chlorine. You see the chlorine ends up with the electrons. So the head of the curved arrow should either show the formation of a bond or the formation of a lone pair. So here we have, again, our nucleophilic attack with the first arrow. And this is going to be forming a new bond. What bond is being formed? This bond right here. And the second arrow, the loss of the leaving group, is showing the formation of a lone pair. So again, the head of the arrow shows the formation of a bond or the formation of a lone pair. And make sure, rule 3 here, the head of the curved arrow does not give you something that exceeds the octet rule. So you can't just leave this single arrow here. That's why we had to show that second arrow showing the loss of the leaving group so that we don't violate the octet rule. Don't forget about your hydrogens. And finally, the curved arrow should be one of our 4 patterns that we discussed: nucleophilic attack, loss of a leaving group, proton transfer, or a carbocation rearrangement. So with this same reaction, again, we have nucleophilic attack and loss of a leaving group in one step. And below, you can see that this is not one of our patterns. It does not match one of our patterns. We're not talking resonance patterns. These are the mechanism patterns that we're learning here in chapter 6. This is not one of our patterns. So that's, you would not push this arrow in that way. So the first skill we talked about was identifying the patterns by looking at the arrows, picking out which 4 patterns goes with what set of arrows. Now the next skill is filling in the arrows by looking at the transformation. So we're going to fill in the necessary arrows. We're going to call this step 1, step 2, step 3. Going from our first set of molecules to the second molecule, we see that we formed a new bond between the oxygen and the carbon. So it looks like we've got a negative charge, that's a nucleophile, and it looks like here that oxygen is making a new bond with our electrophilic site, partial positive. So the nucleophile attacks the electrophile, But if you leave it like this, you're going to end up with a carbon exceeding the octet rule. So we're going to have to push the electrons somewhere else. Now we're going to try to avoid breaking any single bonds here because I have a pi bond that can dump the electrons onto the oxygen. You see that pair of electrons that ended up there? So we formed a new bond, and that second arrow showed the formation of that lone pair of electrons. So step one, this was nucleophilic attack. In our second step, let's look what's going on here. It appears as if I'm taking one substrate and forming two. And it looks like this bond is breaking. And it looks like the electrons that were on the oxygen have now been pushed down to form a carbon-oxygen double bond. So let's push those electrons down and add them to bond. And now this pattern looks like a loss of a leaving group. The tail of the arrow is going to start on the bond, and I'm going to dump those electrons onto the oxygen. See, we've got a pair of electrons that we just put on that oxygen that now has a negative charge. So this second pattern is the loss of a leaving group. Going from the third substrate to the final substrate here, it looks like this hydrogen is being transferred to the oxygen. Well, this can only mean one thing. When a proton is switching places from one to another, we call that proton transfer. This is the same pattern. It always requires minimally those two arrows. The substrate acting as a base attacks the hydrogen, and then make sure the tail of the arrow starts on the bond and it heads to the atom that's getting the pair of electrons. This is proton transfer. Step 3. So in section 611, we're going to look at carbocation rearrangements in a little bit more depth. Every time you see a carbocation, you have to ask, will it rearrange? And carbocations will rearrange if the formation of a more stable carbocation is possible. If you recall, the order of carbocation stability was methyl, then primary, then secondary, then tertiary. Least stable and most stable. So first we're going to identify all adjacent carbon atoms. We're going to look at anything capable of shifting and then determine which of these things will yield a more stable carbocation. Well, if you look at the example below, we've got a secondary carbocation. The carbon with the positive charge is attached to two carbons. That's why it's a secondary carbocation. I'll say that again. The carbon that has the positive charge is attached to two other carbons. That's what makes it secondary. So let's look at our adjacent atoms. I've got hydrogen, hydrogen, methyl, and hydrogen. Now we have to determine if any of these shifting will give us a more stable carbocation. So let's draw a few until we get to something that looks good. Let's shift that hydride. I end up with that hydrogen came up here, and my positive charge switches over here. Remember, there was already a hydrogen. There's your CH3 and your H. So I went from a secondary and I just made another secondary. That's not doing us much good. What if I shift the methyl group? If I shift that methyl group, the methyl trades places with the positive charge, and I form another secondary. That's not doing us much good. So now let's take a look. What if I shift the hydride there? I end up with that hydride that moved, and the positive charge ends up where the hydrogen was. And this is a tertiary. So I started with a secondary. I did a hydride shift and I got a tertiary. This is more stable. So this is the correct shift. This is the correct product that you would draw. These are not correct because I end up with a secondary which is no better than the secondary that I started with. Let's look at several more examples. For each of the following carbocations, we're going to determine if they'll rearrange. If so, we're going to draw the rearrangement product along with the curved arrows. So in the first one, we've got a secondary carbocation. And now we're going to look at the adjacent atoms. I have 2 hydrogens, and I have 2 methyls. Imagine switching, let's look at the hydrogen. If I switch places, if I take the positive charge in the hydrogen and switch places, then I end up with a positive charge here. And that would just give me another secondary carbocation, not doing us any good really. But if I methyl shift, I end up with my positive charge over here, and this is a tertiary carbocation. So that would be the correct shift. Now, the only thing that's more stable than a tertiary carbocation, and this is in your notes, the only thing that's more stable is so if you have a tertiary, an allylic or benzylic tertiary. So an allylic just means your carbocation is in the allylic position. So here, let's look at our adjacent atoms. I have hydrogen, hydrogen. I've got a tertiary, and I've got methyls. If I move the hydrogen, I'm going to end up with a secondary. That's not giving us a more stable carbocation. But if I move this methyl, I end up with another tertiary, but it is also allylic. So tertiary allylic beats a tertiary, irregular tertiary. Now I'm not going to give you examples of scenarios where you have to choose between a secondary allylic and a tertiary. It's either going to be tertiary or tertiary allylic or benzylic. A benzylic carbocation looks like this. Still allylic. They're basically carbocations in the allylic position to a pi bond. All right, in this example, we have a secondary carbocation. Adjacent to the carbocation are hydrogens. So if you can imagine the hydrogen switching places with the positive charge, we'd still end up with a secondary. So this one is going to give us no shift. And now I have at the bottom, I have a tertiary carbocation. And the adjacent atoms have a bunch of hydrogens on them. Hydrogen, hydrogen, and a CH3. I'm not going to do any better than a tertiary here, so this one again has no shift, right? If you move this, you end up with a primary. If you shift this one, primary. If you shift this one, secondary. If you shift the methyl, you end up with a primary. So none of those shifts will beat a tertiary, therefore no shift occurs here. For these ones, let's do the same thing. I have a secondary carbocation and my adjacent carbons. I have some hydrogens. And I've got 3 methyls. If I move the hydrogen, I end up with a primary, which is not better than a secondary. But if I move a methyl, I get a positive charge on the carbon on the left, and that's a tertiary carbocation. So that's better than a secondary. It's more stable. All right, and then the last example here, I've got a primary carbocation, and the only adjacent atom is a carbon that has 2 hydrogens. If I hydride shift, I end up with so this already had 2 hydrogens on it. Now I shift it and it's got 3. I end up with a secondary benzylic, which is much more stable than a primary carbocation. So you're going to need to practice these problems. Please try the ones in the homework. And there's skill builder problems, practice problems, application problems, and then some challenge problems. So I would start with the skill builder problems that are embedded in the chapter and work through those. And you'll get the hang of these.